Welcome to section 5.6, part 1. This is the 59th session of the ISACA CISA exam prep series. In this session, we'll cover the foundations of data encryption. We'll answer several questions. What are the building blocks of encryption? How do symmetric and asymmetric systems differ? What is a hash, and how is it different from encryption? What newer cryptography is emerging? And how does a digital signature prove who sent something? Why does this matter beyond the exam? Because encryption is the last line of defense for your data. Picture a law firm sending confidential contracts over the internet. If those messages are intercepted, encryption is what keeps them unreadable. But here's the catch. Misconfigure it, and the protection you think you have isn't real. So as an auditor, you check the scheme is sound and the keys are protected. Let's start with the basics. What is encryption? It's converting readable plaintext into scrambled ciphertext. Only the right key can turn it back. 3 elements matter. The algorithm is the mathematical function that does the scrambling. The key is the secret that makes each result unique. And the key length determines how hard it is to break. The longer the key, the harder the attack. So how do attackers try to break it? The simplest way is brute force. They try every possible key until one works. Because effort grows exponentially with key length, a long key wins. A smarter attack is cryptanalysis. That's the science of finding weaknesses in the algorithm itself. One more thing matters here. Keys must be truly random. A key based on a guessable password weakens even a strong algorithm. Now the big divide. What's the difference between symmetric and asymmetric encryption? Symmetric uses one shared secret key for both locking and unlocking. It's fast and efficient, ideal for bulk data. But the key must be shared securely, which is the hard part. Asymmetric uses 2 keys that work as a pair. One is public, one is private. You encrypt with the public key and decrypt with the private one. That solves the key distribution problem, because the public key can be shared openly. The trade-off is that asymmetric is slower and more complex. There's a third building block that isn't really encryption. What is a hash function? It turns any input into a fixed length value called a digest. And it's one way. You can't reverse it back to the original. Its power is detecting change. Alter even a single bit and the hash comes out completely different. So how does hashing differ from encryption? Encryption is 2-way and protects confidentiality. Hashing is 1-way and verifies integrity. Encryption uses keys, hashing doesn't. To check a message hasn't changed, you compare the digest you computed with the one sent. Where do you apply encryption on a network? 2 main approaches. Link encryption protects all traffic along one channel, including the headers. But it decrypts at each hop, which creates exposure points. End-to-end encryption keeps the message encrypted from source to destination. No intermediary can read it. That makes it more secure, though the routing headers stay visible. A familiar example is a private messaging app. Let's look closer at the symmetric family. What are its strengths? Shorter keys and far less processing power. That makes it perfect for encrypting large volumes of data. Its weakness is distributing the shared key safely. And it can't sign documents because the secret is shared by both sides. Now the asymmetric family. Why was it invented? Mainly to solve key distribution. With public keys, there's no secret to protect during exchange. The most famous scheme relies on the difficulty of factoring huge numbers. Its drawback is long keys and heavy calculations. That drawback led to newer approaches. What is elliptic curve cryptography? It's a public key system based on the math of elliptic curves. It reaches the same security with much smaller keys. That means faster operations and less bandwidth, a natural modern successor. What about quantum cryptography? It uses the laws of physics, sending data as individual particles of light. Its magic is detection. Any attempt to observe the data changes it, so eavesdropping is caught instantly. But it's costly and works only over limited distances. And what is homomorphic encryption? It lets you compute on data while it stays encrypted. You never have to decrypt to process it. That's powerful for cloud and supply chain security. The catch is that it's slow and resource hungry. Now a capability that builds on public keys. What is a digital signature? It runs the public key idea in reverse. The sender signs with their private key. Anyone can verify with the matching public key. In practice, you hash the document first, then sign the digest. A digital signature delivers 3 guarantees: integrity, because any change breaks the hash; authentication, because only the sender holds the private key; and non-repudiation, because the sender can't deny it later. To stop a replay attack, attach a timestamp. So let's bring it together. Encryption scrambles data, and the key length sets its strength. Symmetric is fast, but hard to share. Asymmetric solves distribution, but runs slower. Hashing is one way and proves integrity, not confidentiality. Newer methods like elliptic curve and quantum push security further. And a digital signature proves who sent a message and that it wasn't changed. Master these foundations, and the applied cryptography ahead will make sense. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.